I actually looked it up. The whole like wet friction thing. I don't think actually it was correct. I don't think it's just called wet friction. It seems like wet friction is the car and the air seems to be like the wet friction part, and dry friction seems to be two surfaces rubbing against each other. So I guess like the car going would be sort of a combination of wet and dry friction. I don't know. I'm not a physicist. I just like heard someone talk about wet friction. I was like, that seems like my thing. So yeah, don't quote me on that. Don't do it. Do as I say, not as I do. It's not the. I guess that doesn't apply here. Whatever. Anyways, let's move on. So let's implement this other friction model that I called wet friction, but I don't think it's called that at all. But the cool friction, there we go. We'll call it that. We're doing cool friction. All right. Since friction in this case is going to be relative to the size of the speed, we're actually going to remove just this get safe normal here. We're only going to do that our friction is minus velocity times some friction constant. Alright. So I can say right now that 100 is quite a lot. So like this is quite a huge amount of friction. But let's see what happens. So I'm just gonna start the game and see. Okay, so it worked. So we are going. Oh, I didn't compile. I was like, that's way too fast. That's not how fast we're supposed to be going. Okay, so now let's see. Okay, there we go. So this is what I expected. We are moving, but we are moving so fucking slowly. Like you can see, we are barely snailing forwards. And that's because this friction constant is way too high. So a friction constant, in this case, in this sort of model of friction, around 3 is like really fast. It's like it will almost stop immediately. Around like 0.5, then we're talking like, okay, sort of ice physics ordeal. So I'm gonna do it around 0. I'll do like 0 point. Like it doesn't really like there's no number. Like there's no intuitive way to sort of fill these numbers out. Like this 0.9 doesn't really mean anything on its own. But it's sort of more of a you tweak this until you make it feel nice. So I'll do around 0.9. Let's see what happens now. Alright, so this is a pretty good speed, I think. So now you can see as I'm accelerating, I'm reaching a max speed. And then I'm just sort of staying at that speed. So I'm not accelerating further than when the friction and the acceleration is the same. So there's going to be some speed where our friction is 200 essentially. Some speed our friction is going to be our like velocity times 0.9 is going to be 200, and then it's going to cancel out the acceleration and we're just going to stop gaining speed. Very cool. So now we have that. That was very easy. So now let's make it so we can turn, alright? I think that makes sense. So I'm just gonna add in the turning here and let's see what happens.
Is it still so that when you let go, it will slow down and stop by itself with friction?
Yes. So when you let go, it will still slow down. And it will slow down fast at first, and then it will sort of start rolling, and then after a while it will stop. Because again, the friction becomes lower the slower you go. So as we're slowing down, our friction is actually slowly decreasing as well. So that's why we're not sort of linearly slowing down and then stopping. We are sort of like fastly slowing down and then rolling a little bit until we come to a resting state. Very cool. And I want to again emphasize that this is not like real physics. This is like, an approximation and we're influenced by physics, but I wanna really hammer home. This is not exactly how physics calculations works. They are much more complicated and much more nuanced than this. But we use analogies. We're using the analogy of friction, and in gameplay, that's almost always good enough. Cool. So let's turn. Let's turn our urn. So I'll do add actor world rotation. So I'll just make a rotator. So we'll want to again yaw. So I'll do 0. Oh dear. 0. And then we'll do our turn rate. What would I have, like 90? Yeah, 90. Let's go 90. Again, I'm hard coding this because I'm a good programmer. Don't you dare say anything otherwise. So I'll do 90 times turn right input. Whoops. Times delta time. Oh, added active world transform. Whoops. Rotation. Okay, so let's compile. And let's see what happens. Oh, my controller died. So I can turn. And now it's kind of... Okay, so this is cool. So it's kind of like we're... It's kind of like we're racing on ice. Or like we're a hover car or something. Yeah, it's kind of like we're playing asteroids. So as I'm turning, I'm accelerating, you know, in the way I'm pointing. And then I'm like slowly turning that way. Because I have like remnant velocity going in the other direction. Cool. So we should probably make it so that if I have velocity going in the parallel direction, not parallel, sorry, the perpendicular direction. So if I'm turned this way, because if we're thinking about it, when I'm going forward, the friction is going to be less because the wheels are rolling, right? And since the wheels are rolling, that's reducing friction. Because, you know, the car is not sliding against the ground. There's actually wheels turning, which makes our car go forward, amazingly. But as we're perpendicular to the direction like this, then we should be stopping way faster because our wheels are not turning anymore. They're actually sliding against the ground. So that means we should be experiencing much more friction in the perpendicular direction to the car than in the parallel direction to the car, because there the wheels are not turning; they are sliding against the ground. So we're actually gonna use 2 friction values. We're not gonna have 1 friction. We're actually gonna have 2 friction. We're gonna have parallel and we're gonna have perpendicular friction. So the parallel friction is gonna be the friction of the gears in the car and the wheels against the road, rolling, and then the perpendicular friction is gonna be, you know, the car resisting to going in that direction because the wheels are actually gripping the road and sort of, you know, stopping the car from going that way. So we're gonna make 2 friction values. We're actually gonna split the velocity into 2 values. So we're gonna split the velocity into parallel velocity and god damn it, perpendicular velocity. There we go. So how do we do this? So if we have our car, right? So here's our car. That's a good looking car. And this is the forward vector. So if we have a velocity going like, this way. Come on. Going this way. Then we want to split this into two parts. So we want to split this vector up. So we want to have the part of the vector that's pointing straight forwards. So we're going to split this vector into its forward component. So this is the component of the vector that's pointing alongside or parallel to our direction of our car. And our perpendicular part that's pointing away from the car. So we're going to split the velocity up into two parts. And you can see that these two added together, so if I add these two vectors together, we get back to where we were. So these two sums give us the whole thing. So we're just splitting it up into two parts. And then we're going to decrease them separately. So we're going to decrease this, we're going to apply a force to this velocity separately from the force on this one. So that's going to be our two friction values. Cool. So to do that, we want to get the vector that's alongside our forward vector to get the parallel velocity. And luckily there's a very nice helper function for that. So we can just use that. We could use our mathematics, we could do our dots and our normalize and our things. But there's a very nice helper function that's just velocity constrain to constrain. Doesn't it exist?
Is it a static method, perhaps?
Oh, maybe it is. What is an fmath? Did we make that ourselves? Because we have it in Hayslide. Maybe we made that ourselves. I'm not so sure it existed. Constrain to plane into direction. I can swear to God I've used it. Alright, whatever. Never mind. We don't have a helper function. We gotta do it ourselves because we're fucking sick. Okay, so how do we do this? How do we get the part of the velocity that's pointing in the forward vector? Channel your, go into avatar state and talk to Freya. And ask, what would Freya have done?
Getting the
Just ignore
forward
the other
vector.
axis, right?
Sorry?
Don't we just ignore the other axis? Like just take the x-axis of the velocity vector.
We could do that if the velocity was in local space. But since, the velocity is in world space, and our car's forward
Yeah, but
vector...
then we can just take the one that is pointing in the forward direction, right? There.
Well, in this case, if we say okay, if we take the world axis, then this is x, and this is y, then the forward component of the velocity is not actually pointing in any one axis. It's not pointing in the x or the y axis directly. It's pointing in sort of a combination of x and y.
There is a project method.
Project.
Or project onto it.
Isn't it just the dot between?
Oh, there it is. Project onto normal. Why is it called that? Okay, there is a function, but we're not gonna do it because I see that you guys need to revisit this anyways.
Isn't it just take the dot between the velocity and the forward vector of the car?
Yes, exactly. To project a vector onto a normal. So if this is our f, I'll do f hat, and this is our v. Then we do v dot f. This will give us the length here. This will give us how much of the vector, what's the length of the vector lying on f. So how much of the vector v is aligned with normal f. That's what v.f will give us. So this will give us a scalar, and that will be the length of the vector. And to then get the vector itself, we multiply this. I'll do next. We'll multiply this by f. And that will give us this vector here. So I'll do it, call it v dash. So to project a vector onto a normal, we do v dot normal. It has to be normalized. That's why I have the hat here. So v dot hat f hat times f hat will give us the projected vector onto the normal.
What do you mean v dot f? The dot part. Is
That's
that
dot.
Is that multiply or?
That's dot product.
Oh, dot product. Okay.
Yes. So when it's a dot, it's dot product, and when it's a cross, that means cross product. So v dot f times f. That's the projection function or projection formula. So we'll do that. We'll do velocity dot product. Okay, never mind, it's a static function, so we have to do that. So we'll do f vector dot product. So we'll dot product velocity with the forward vector, so get actor forward vector, and then take that times get actor forward vector. So that will give us the part of the velocity that's pointing forwards. And then to get the other part, I will just do the same thing, but instead of the forward vector, I'll just do the right vector. So I'll do velocity with get actor right vector times, times get actor right vector. So this will give us the part of the velocity that's pointing in the actor's right vector. So now we have our two velocities. We've split them up. One part is going to have the wheels rolling, so we'll have less friction, and one is going to have the wheels dragging, so it's going to have way more friction. So I'll just make two friction values out of this. So I'll just do vector parallel friction. So that's going to be two forces. So the parallel friction is just going to be the minus parallel velocity times some small constant. So it's going to be, yeah, let's do our 0.9. I thought that was a pretty good constant. So that's going to be our friction constant for wheels running, wheels spinning. And then we're going to have a larger perpendicular friction. We're going to have a larger friction for our perpendicular velocity. So that's going to be minus, perpendicular friction times, let's do like 2.1. Yeah, sure. That's a pretty large friction. So now we have our two friction values. We have two friction forces, one parallel and one perpendicular. So instead of having one friction that we add here in the velocity, I'll just remove this for now, so we don't have the regular friction anymore. I will just add these two together. So I'll just add the parallel friction. Whoops, not parallel, let's say parallel friction, and plus the perpendicular friction. There we go. So now we're applying.
I think, on where you set perpendicular friction, you accidentally wrote perpendicular friction instead of perpendicular velocity.
Oh, thank you. That would have fucked me over so hard. There we go. Thank you.
Isn't parallel velocity the same as velocity at this very moment, at least?
It's the same until we turn.
Right, but we already get the actor forward, so isn't that still just a velocity in world space?
What do you mean?
Because I mean the velocity before, wasn't that compared to the actors forward already? Or wait, did you multiply that somewhere? which you removed. I don't know. No, because acceleration is already forward.
Yeah, that's acceleration. But the velocity is something else.
Right.
So we're all
Oh,
actu-
yeah. Never mind.
We're accelerating
cool.
forwards,
Yeah.
but our velocity can point in any direction.
Gotcha. Cool.
So let's see what happens. I'm genuinely curious. I've actually never made a car like this, so it will be interesting to see what happens. I made many vehicles, but a car is not one of them. So we'll see what happens. We'll take it as we go. So now, as I turn like this, I'm actually skidding in, and you can see that the car is actually kind of turning, right? You can see, like, if I go fast and then I turn, do you see that the car is sort of curving to a stop? You see that? So that's a nice little side effect, because that's kind of what we expect, right? If I turn like this, we expect the velocity to kind of curve into the turn, right? And that is because we're splitting up the friction. So we're applying a greater friction. So like I'm like sort of like, here's the car, right? My phone is the car. I'm like going forward, and I'm like sort of like, you know, drifting like this. We're applying a greater force this way than we're doing that way, which means there will be a little bit of velocity still there. I'm not like totally 90 degrees. I'm like sort of skidding in like this, so I still have some forwardness pointing to where I was going, and that forwardness will stay longer in the velocity than in the perpendicular direction like this. So that means, you know, as we're slowing down this way, there will be a great force slowing us down this way. The force going forward, or the velocity going forward, will actually stay longer, which means we'll start to go upwards a little bit. So that's cool. So that's a neat side effect of splitting it up like this. So now, as I'm going around, you know, we're sort of always drifting right now. So we probably want to tweak our values a little bit, so we're like not always drifting. I will probably like increase the acceleration a little bit, probably, and like maybe increase the friction as well. But we can do that later. So, but now at least we have like a better, like, I feel like this is like sort of, it's a car, right? Like right now we're sort of have something resembling a car going on, so that's pretty cool.
Could you just show the like parallel velocity and where you set those one more time? I think I missed something there.
I can upload this project over the lunch as well.
Nice. Yeah,
So you can have a look at it.
it would be great.
Cool. Any questions on this so far?
Yeah, sure. I have a question. It's about the wet friction constants or whatever. So you say there's like, so in my head, this means that you add, because you add them together, right?
Yes.
Yeah, exactly. You add that to the acceleration. So perpendicular friction would be your velocity in perpendicular times 2.1, and then you add that together, so it would be like 2.1 of your perpendicular velocities in the other direction.
Yes.
Wouldn't that just make you stop and go in the other direction, like instantly?
Well, we're doing delta time. So
Oh, yeah, true.
So we're not adding 2.1 instantly. We're doing 2.1, but we're adding it in delta time, which means that it will. But yeah, if we had a delta time that was bigger than 0.5, then yes, we would get like, it will explode.
Okay.
So that's why this, again, why this is sort of like, it's not like this in physics, because you know these values will explode if we have two extreme values. Like if we have like 1,000 here, then it will sort of explode and it will start to jitter and it will start going crazy because like the values are way too big. Or if delta time becomes too small, then the simulation becomes way too coarse and we start exploding, like you said, like we will start flipping the velocity downwards and stuff like that. And that's where we have to start like integrating the values, and we start having to do like fucking blah, 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 mathematics and whatever.
Yeah, but okay, so one way of thinking of it is that if it's times 1, then we can't the acceleration can't beat out the friction, then they cancel each other out, right? Because then if you're accelerating by like the value times 1 and the friction is counteracting that times 1, then they should cancel each other out, right?
Yeah, you can sort of see this number as when they will cancel each other out.
Okay.
So if we have, let's say if this was 1, right? So if for the parallel we have a friction of 1, that means when we're moving at 200 velocity, friction will be minus 200.
Yeah.
And since acceleration is 200, that means at 200 we have reached our max speed, because at that point acceleration and friction are going to be equal.
Yeah.
But if we have a friction of 0.5, that means at 400 velocity we're going to have a force of minus 200. Right? Because we're timesing it by 0.5.
Oh, yeah.
So that means at 400 our friction is going to be equal to our acceleration. So our max speed is going to be 400.
Right. So it's how much you accelerate times the friction constant is your max speed?
Kind of, yeah. Kind of.
Okay.
It's yeah. They control sort of both.
Cool.
Like, if you want to make you reach the max speed faster, then you have to sort of tweak both.
Yeah.
So that the acceleration times the friction constant sort of, stay in the same proportion. But yeah, like they both control your max speed, because if you add acceleration, then your max speed goes up. If you add friction, your max speed goes down. So you have to sort of like you raise them up and raise them down, sort of tweak those two values sort of to get the max speed you want.
Yeah.
But yeah.
And if you're like getting nitty-picky, then acceleration is also not just a value, but like the force added divided by the mass of the object. And then that object will also, like the mass would also influence the friction.
Yes. Yeah, we could have something like mass, yeah.
But I mean, it's just an extra step instead of writing that we just have. Like now we're setting throttle input being the acceleration basically, instead of just calculating the acceleration first. Because we don't have mass on we don't use the weight on the vehicle, right?
Yeah, no.
Which we don't need unless we're like bouncing off each other and the heavier one would punch the other one.
Yeah, we could do like weight and stuff, and then absolutely, then we would include that in our like velocity prediction here, or velocity acceleration stuff here. We would take like mass and inertia into account, so massive stuff will go slower and so on.
Let's say that for later, I think.
Yeah, let's not do it now.
It was just a parenthesis.
Yeah, but that would only be for friction, right? It wouldn't be for adding velocity.
Yes, because that's like that. First you calculate the acceleration out of the force, and then you use the acceleration to add to the velocity, and then you use the velocity to add to the where the body is going, basically.
Yeah. No, sorry, I was wrong. It's that's only for gravity. Yeah, but let's take lunch.
Yeah, yay, hooray, lunch. Yeah, okay, so
We don't
let's
want to
take lunch.
create any more friction here.
Yeah, I'm feeling the friction going on. Yeah, so let's take lunch, and after lunch we'll maybe do collisions. I would say collisions sounds fun, something like that.
Yeah.
We'll see where it goes, but yeah, let's play around with this. I think it will be fun. So yeah, I'll upload the videos, so you can play around at lunch if you want to. Let me know if you want some more time to sort of play around before we continue. We can maybe start half an hour later or something if you feel like you want to play around with it. You can just poke me in Slack or Discord, for that stuff. So yeah, I'm flexible.
Awesome.
Cool. So see you guys after lunch.
Yeah. See you
Bye-bye.
soon.